I'm going to start this by trying to analyze the fiber to air critical angle. The fiber to air critical angle. So to find any critical angle, we make the angle of refraction 90 degrees. Okay, so that's kind of the formula to find the critical angle, where theta c represents a critical angle. Now we're going fiber to air. So we know that the index of refraction for air is 1. So the right side of the equation is actually just 1. I'll actually label this as NF for index of the fiber. So then isolating for the critical angle, it'll be the inverse sine of 1 over the index of refraction. We are told that the index of refraction is greater than or equal to 1.42. Therefore, the critical angle I'm going to go back a couple steps. Just want to make sure. So the denominator is 1.42 or bigger. So the denominator is 1.42 or bigger. Therefore, the fraction as a whole will be less than or equal to 1 over 1.42. And then I will use the inverse sign now. So the critical angle is going to be less than or equal to, let's do this in the calculator, 44.8 degrees. I'm going to keep a couple of extra digits. 44.767 degrees. Okay. Now, I want to try to analyze gamma. This angle here. I have to show that that angle is going to be bigger than the critical angle, and therefore total internal reflection happens. So I'll say that therefore we need to show gamma is greater or equal to this value. So that total internal reflection, TIR, happens. Okay, so let's try to find gamma. To try to find gamma, I'm looking at a right angle triangle. I'm not sure. I'll draw it out in yellow so that you can see it. So if I take this horizontal line, connect it with this vertical line, and connect it with this red line, the light beam, we get a right angle triangle. And in that right angle triangle, the angles have to add up to 180 degrees. Like all triangles, the angles have to add up to 180 degrees, unless, of course, the triangle is on a curved surface, but we're on a nice flat geometry here. Therefore, I subtract 90 on both sides. Gamma will end up being 90 degrees minus beta. So I'm just going to keep that in mind. I'll call that equation 1 perhaps if I want to refer back to it later on. But I need to find out, in order to find out something about gamma, I'm going to need to find out something about beta. And I can actually use Snell's law with light coming from the air on the left into the fiber optic. So Snell's law for the air to fiber on the left of this diagram. Okay, so we'll have n1 sine theta 1 equals n2 sine theta 2, Snell's law. On the left side, the index of refraction for air is 1. Well, we're just going to use 1. The angle of incidence has been labeled as alpha. And on the refraction side, the index of refraction is at least 1.42. So I'm just going to write index of the fiber for now times sine of the angle of refraction, which they've labeled as beta. However, this is greater or equal than 1.42 times sine of beta, because we are told that the index of refraction is at least 1.42. Okay, so doing a little rearranging here, dividing both sides by 1.42, we will get sine of alpha over 1.42 is bigger than or equal to sine of beta. And here is where it gets quite tricky. Got to think outside the box here. What I'm going to do is declare that the maximum value of beta is the inverse sine of 1 over 1.42. So that's the biggest possible value that beta can be, because sine of alpha in the numerator here, the biggest possible value for that is 1. The sine function is always between -1 and 1. Okay, so what I'm saying is that beta at a maximum can be inverse sine of 1 over 1.42, which is 44.767 degrees. Now I'm going to take that expression and put it back into equation 1. So equation 1, we had gamma was 90 minus beta. But beta can at most be 44.8. I'll just go 44.8. Beta at most is 44.8. So since beta is at most 44.8 degrees, then gamma is at least So it kind of flips. It is at least 90 minus 44.8. So gamma is at least, that makes 45.2 degrees, which is greater than the critical angle, because we found that our critical angle is at most 44.8. Okay, so you may have to think a little bit about how it turned from beta is at most 44.8 to gamma is at least 90 minus 44.8. So this beta value, if we sub in 44.8, then 90 minus that is 45.2. Beta cannot be anything higher than 44.8. So what if beta was a bit less? What if beta was 43 degrees? Then gamma would be 90 minus 43, which is 47 degrees. So actually, gamma gets bigger as beta gets smaller. So they've got the numbers working out such that no matter what, gamma is always going to be bigger than the critical angle. So it will always have total internal reflection. Therefore, fiber optic cables must always have index of refractions of at least 1.42.